Hello, and welcome to our presentation, Data Acquisition, Analysis, and Visualization of Muon Tomography in the El Castillo Pyramid at Chichen Itza, Mexico. Millions of cosmic rays, consisting of high-energy atomic nuclei like protons, strike Earth's atmosphere every minute. The formation of cosmic rays is still an area of ongoing research. One way cosmic rays are believed to be formed is through supernovae. Massive stars that end their lives in a powerful explosion known as a supernova can release enormous amounts of energy, accelerating particles to very high speeds. Another way cosmic rays may be formed are active galactic nuclei. Active galactic nuclei are highly energetic regions at the centers of galaxies where supermassive black holes accrete matter and generate intense radiation and particle jets. When these primary cosmic rays reach Earth's atmosphere, they interact with the air molecules, primarily oxygen and nitrogen particles, to produce a shower of secondary particles. Among the secondary particles created in the air shower, there are short-lived subatomic particles called pions. These pions are produced in great numbers. Pions are unstable particles and rapidly decay into other particles. The most common decay mode is when a positive pion decays into a muon and a neutrino. Muons are subatomic particles that belong to the group of elementary particles known as leptons. They are similar to electrons in many ways, but are more massive. Muons are considered fundamental particles, meaning they are not composed of smaller constituents. A muon's lifetime is approximately 2.2 microseconds, which is relatively short compared to many other subatomic particles. After being created in cosmic ray interactions with Earth's atmosphere, muons travel at nearly the speed of light due to their high energy. Despite their short lifetimes, muons can reach Earth's surface from the upper atmosphere. This is made possible by a fascinating phenomenon called time dilation, a consequence of Einstein's theory of special relativity. As muons travel at speeds close to the speed of light, time appears to pass more slowly for them, relative to an observer on Earth. This time dilation effect allows muons to live longer from their perspective than what is observed on Earth. Consequently, even though their lifetime is only a few microseconds, they can travel significant distances in the upper atmosphere before decaying. By the time muons reach Earth's surface, they have traveled through tens or even hundreds of kilometers of atmosphere, defying their short lifetime and making them detectable by ground-based muon detectors. Muons are also known for their high penetrating power, allowing them to pass through thick and dense materials. Unlike other particles, muons can travel through solid substances such as rock, soil, and even metal without getting absorbed or scattered significantly. Muon's natural abundance and ability to penetrate through dense materials to reach Earth-bound detectors makes them useful for a technique called muography. Muography is a non-invasive imaging technique, like an X-ray. However, muons have 1,000,000 times more energy, allowing them to go through and image much more material. Muons can interact and be stopped by some of the material, causing a decrease in muon rate. Using detectors to measure the rate of muons from different directions can tell us how much material was in the way. Muon detectors will be placed inside the El Castillo Pyramid at the World Heritage Site in Chichen Itza, Mexico, to non-invasively determine the pyramid's internal structure. We already know that the current El Castillo Pyramid was built atop a second smaller pyramid. The ultimate question of this research is to determine if there is a third, even earlier pyramid within the second pyramid. The muon detector to be used consists of 3 detection planes. Each plane has 2 sets of triangular muon detection channels laid perpendicular to each other. Through seeing which triangles detect a collision and the intensity of their activations, the muon's path can be determined. As shown in the 2D diagram to the right, using triangular channels allows each muon to potentially pass through multiple channels at once. Based on the intensity of the collision as detected from both channels the muon passed through, the relative intensity of both channels can be used to more precisely determine the exact position the muon passed through. Our project aims to create a dynamic and informative website, serving as the central hub for this exciting endeavor. Here's what our website brings to the table. Documentation for the public. We documented this experiment, making it accessible to the public. Anyone interested in the project can explore the website to gain valuable insights into the fascinating world of muon tomography and its application within the El Castillo Pyramid. Data verification for collaborators. Our website allows scientific collaborators to access and verify the quality of the data collected. This will help demonstrate that the data collection is working properly, aiding in the commissioning of the detector later this year. Visualization of the experiment. To make the intricate techniques understandable, we present 3D and 2D visualizations of the experimental setup and muon detection events. These visuals offer an immersive experience to better comprehend the experiment's interworkings. Data analysis tools. Our website offers powerful data analysis tools, including histograms and charts, enabling scientists to assess the detector's functionality quickly and efficiently. In order for our website to function, we must be able to read the data generated from the detector. As the detector is not yet active within the pyramid, we simulated what the proper data would look like in order to create the necessary programs to interpret this data. Each plane of the detector will be connected to a separate data readout box. All of these boxes will communicate with the computer to create data files. Unfortunately, each channel has noise, which could be mistaken for a muon detection. This noise must be removed from the data file for proper analysis. For each channel, a frequency graph can be made, showing the frequency of different readings from that particular channel. The readings that are noise create a smaller peak representing the average noise. The average noise, called the pedestal, is measured and saved in a pedestal file. Each channel has its own pedestal value. Our website needs the intensity values of all channels hit during each muon collision event to create displays and analyses. Therefore, I read the signals from every channel, subtract the respective average pedestal value from each channel, then set all channels that do not meet the minimum threshold of activation to 0. I then convert the activation of every channel in each layer for all events in the data files into a 3-dimensional array that can be used throughout our website. I read the 3-dimensional array I generated to find the number of times each channel activates in each layer. This allows for the creation of histograms for each layer of triangles in the X and Y direction. The finalized histograms, when studied with thousands of events, can find incongruities and potential issues with the channels. The ADC analysis graph creates a scatter plot of adding the activation of adjacent pairs of channels where both channels are activated. This graph is used for quality control. Due to the channels being triangular, each muon collision passes through 2 triangles. The total intensity of each muon collision should remain constant throughout all of the channels. Therefore, adding together the values of neighboring channels that both detect a muon event and placing this data on a scatter plot lets us view the total detected intensity of each collision across all the channels to ensure it remains constant. Experimenters must adjust the gain for each channel based on temperature, as temperature can impact the sensing intensity. This graph allows experimenters to visually see how gain must be adjusted to keep the detection intensity values constant across all of the channels. Our website's 2D visualization capabilities allow website users to clearly see how a muon track is generated from the 3 sets of detection planes consisting of channels laying perpendicular to each other. Users can scroll through events and see the generated muon track on both axes for each event. Thank you for your time so far. I would like to thank all of the collaborators helping in this experiment. Next, Brian will discuss our website's 3D visualization capabilities.